In this video, I'm going to give an overview of the math module in Python, which is a built-in module that contains the most commonly used mathematical constants and functions, typically found on a scientific calculator. So to use the module, it must be imported, and it's not typically imported as an alias because its name is rather short. So now that it's imported, we can look up its help. And if we view this in the text editor, we can see that it's mainly a module of mathematical functions. And there are some constants. So once it's imported, we can access the identifiers. And we can also print the directory as a list. And we can group this into constants, mathematical functions, and then we've got the data model attributes and methods, which are present pretty much in every Python module. So let's have a look at the mathematical constants and build up an intuition around them. So let's start with a circle. So here we've got a circle, and we've made a circle of unit length, so it means the radius is 1. So the radius is shown in red, and the circumference is shown in blue. So pi is the ratio of the circumference to twice the radius, which is actually the diameter. So we can access this as a constant, and it's a floating point number, and it basically continues on forever, and this is it stored to the limited float precision. So if we rearrange this above equation, we get c equals 2 pi r, and if we divide through by 2 pi, we get r equals c over 2 pi. And this is the definition of a unit known as a radian, which is a normalized unit. That gives the indication of the arc length of the circle. So the circle constant pi, and by extension the normalized unit known as a radian, conceptually makes sense when considering the circle as a whole. However, these units have a drawback that they're not very human readable in decimal form, because you've essentially got all these trailing numbers, and therefore the degree is quite commonly used when humans are interacting with circles. So let's have a look at this circle in degrees. So you've got 0, 45, 90, one right angle, 90, 135, 180, the second right angle, 180, 225, 270, third right angle, 270, 315, and back to 360, which is the last right angle. So because we've got these two measurement units, we need some conversion between them. So there's the conversion function, math.radians and math.degrees. So this basically gives the radians from a degree and gives the degrees from a radian. So we can see how many radians for 1 degree. And we can see it's a very small unit. And how many degrees are in 1 radian? It's quite a large unit, 57.3 degrees. So if we check how many degrees are in 2 pi, we should get 360. And this works as expected. So there was an attempt to decimalize the degree, making another unit known as a grad, where 100 grads make up a right angle. This unit was never commonly employed because 90 is more divisible than 100. So if you have a look at 90 divided by 3, 90 divided by 6, versus 100 divided by 3, and 100 divided by 6, you can see this is much easier to work with. So in the math module and scientific computing packages in general, the radian is used as a unit of measure for angles in geometric shapes. So conversion from degrees to radians have to be made on angles before using the angle as an input argument for any of the other trig functions. So pi can be defined as the ratio of the circumference to the diameter of a circle. However, the radius is typically a much more important quantity used in calculations. So if we have a look at the circumference, it's 2 pi r. And to get the area, we raise it by a power, so we get r squared, and then we divide by 2. Some people think this is convenient because this simplifies down to this and looks a bit neater, but they may miss the actual process of what's going on in order to get this. And the volume of this sphere is getting raised to the power again and then dividing by the new power. So a single point is typically referenced with respect to the center of the circle using the radius and not the diameter. And due to pi being associated with the diameter, which is twice the radius, the term 2 pi is used frequently as a normalization factor. In the circle above, for example, pi represents only half the circle, and therefore 2 pi represents the full circle. So some mathematicians and physicists argue that the term 2 pi is a much better normalization factor, and this is therefore known as the circle constant tau. So here you can see the value of tau, and tau is therefore twice the size of pi. So using tau instead of pi more clearly depicts the use of integration to calculate the area of the circle instead of masking the division by 2. So here we see what's happening, and if we have a look at the plot of the circle, we can see that essentially it's normalized correctly by tau. So we don't have this random factor of 2 to confuse us. So the radian therefore has the following relationship with tau. Instead of 2 pi here, you've just got tau. And you see this is normalized correctly. So another constant is E, and this is known as Euler's number, and it's an important constant when it comes to modeling exponential growth. So the value of E can be calculated empirically using this formula, and this formula gets expanded out into a series, and this is a factorial. So each of these is a factorial, and the definition of a factorial is 0 factorial equals 1. So it's not equal to 0 because if it was 0, then anything multiplied by it would become 0. So this is equal to 1 and this is equal to 1. Then everything else is 1 times 2 times 3 times all the way to n. So this is 1 times 2, this is 1 times 2 times 3. So a function can be made to calculate a factorial. So the result is going to be 1 if it's 0 factorial or 1 factorial. And if it's higher, then this range function is going to be used to calculate the result. And then the result is going to be returned. So we can run this function and we can test it. So factorial of 0 is 1, factorial of 1 is 1, factorial of 2 is 2 times 1, which is 2. Factorial of 3 should be 3 times 2 times 1, which is 6. So this factorial function can be used within a Euler series to calculate a total. So if we define this function and we have a look at the Euler series of 1, we're going to get 2, and the Euler series of 2 gives us 2.5, and of 3 gives us 2.667, 10 gives us this 2.718, 50, 2.718, 102.718. So basically this number is beginning to converge as the value provided in the Euler series increases. And if we have a look at a plot, we can see you've basically got a lot of difference for small values of factorial. However, when it reaches a certain value, then this essentially becomes a constant number, which is known as Euler's number, or E. And this is the constant math.E. And there's two other constants. So you've got infinity, and you've also got not a number. So if these constants are going to be used regularly, they can be imported directly into the namespace. And the type of these 5 is a float. So the math module has a couple of Boolean functions which we'll check to see if these are infinite or finite or not a number, and return a corresponding bool. So for example, 1 is not infinite, so this is false, but infinite is infinite, so this is true. And is finite, 1 is true because it's a finite number. And is infinity finite? No, because it's infinity. And the number infinity is regarded as a number, whereas not a number is regarded as not a number. So is nan infinity is false, and is nan, that's true. So the math module has a power function which is very similar to the power operator. If the math function is however used on two integers, you'll see a subtle difference when using the power operator between these two integers. So here the type for both of these is an integer, so an integer is returned. Here a float is always returned. The math module also has the function square root and integer square root, which compute the square root and integer square root respectively. So we can have a look at their doc strings. We can test this with the value 16. So the square root gives the value 4.0, whereas if we just use the power to 0.5, we also get 4.0. If we have a look at the integer square root, then what's happened is we actually get the value 4, and there's no decimal point because we're specifying we want an integer. When the integer square root is used on a number, that's not going to give a precise integer. It's going to round it to, or it's going to truncate it to the integer. So here you see the square root of 17 is 4, and that the integer square root of 24 is 4, so it doesn't get rounded up to 5. So next is the concept of combinations and permutations. So the number of combinations and the number of permutations can be calculated using the math.com or math.perm functions respectively. So the doc strings of these may be a bit confusing when you first see them. However, it's better to visualize something pictorially. So basically, if we say n is the number of items that can be placed into k containers. So we've got 2 containers here and we've got 3 items. So what are our combinations? Our combinations a green and a purple, or we've got a combination of a green and a red, or of a purple and a red. And each combination can be thought of as a set. That is a subset of the items from K, and like in the case of a set, the order doesn't matter. In a permutation, however, the order does matter, and in this example, because there are two containers, there are two permutations for each color combination. So effectively, you could have this, or 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 you could have this. So the combination and permutation functions can be used with the above examples. So we've got 3 items and 2 containers. And this gives us 1, 2, 3 combinations. Once again, we've got 3 items and 2 containers. And this gives us 6. The math module contains a number of rounding-related functions. If you consider a floating point number as lying between integer levels, math.floor and math.ceiling will return the integer of the floor and the ceiling. So for example, pi is 3.14 ... and the integer floor of it is going to be 3, and the integer ceiling of it is going to be 4. So scientific notation allows numeric representation for a very small and a very large number. Now under the hood, a floating point number is stored in bits. So each bit can be either off or on, and therefore represented pictorially using an LED. And typically we use the IEEE 754 floating point precision, which uses 32 bits. So we've got 1 bit for the mantissa sign, 8 bits for the signed exponent, and 23 bits for the mantissa. So due to there being a finite number of bits to store a number, and only 2 characters in binary, there are a number of recursive rounding errors, and these occur far more frequently than in the decimal system. However, since you're used to the decimal system, we can conceptualize a recursive rounding error by the concept of a third. So basically this goes on forever, and because we've got a finite number of digits, we need to truncate it. So assuming we're going to use 6 digits after the decimal point, then the effect of chopping off the trailing 3, etc. rounds this down, and the calculation of third plus a third plus a third will give you 0.999999 instead of 1.0, which it should be. And therefore, if a comparison operator is used to check whether this is exactly equal to 1, the result might be false. So such a recursive rounding error exists frequently with floating point numbers because they are encoded in binary. So sometimes it's more appropriate to use the math is close to function to check whether two floating point numbers are close enough to one another, i.e. lie within a specific tolerance. So it's essentially going to compare the numbers A and B using a relative tolerance or an absolute tolerance. So let's have a look at the number 0.3, and we're going to print it out so it's basically using all the digits. We're also going to compare this to the concept of 0.1 plus 0.2. So notice, with all these digits specified, that this number and this number are different. So if we use the comparison operator to check whether the left-hand side and the right-hand side are equal, we're going to get false. If instead we use the math.isClose to function to check whether the left-hand side and right-hand side lie within a relative tolerance of 1 times 10 to the power minus 9, we get true. So the relative tolerance, 1 times 10 to the minus 9, means the number lies within this specified region, and we can see that it does. So is larger than this value and smaller than this value. So the absolute tolerance can also be specified. So we can specify this as 1 times 10 to the minus 6. And once again, this is true. And we can have a look at the lower and upper bound for such an absolute tolerance. And we can see that this number lies between the lower and upper bound. So because the physical arrangement to store the floating point number uses a finite number of bits, a consequence of this is that the smaller numbers are much more closely spaced than the larger numbers, i.e. you're using essentially a relative tolerance between the numbers. So we've got the math unit in last place function, which will return the value of the least significant bit. So if we have a look at 0.1, we've got 0.1 and then all these zeros and then 1. So this is the unit in last place. And if we have a look at the unit in last place, we see that it's essentially this 1 here after all these trailing zeros. So if we add this together, then this should be all these zeros and then a 2 here. And we see this works as expected. So if we take a large number, so this one has a lot of zeros before the decimal point, and we have a look at the unit in last place, we see we've actually got a massive number. So this is 128. So it's not massive compared to this number, but 128 compared to this number is very, very large. So if we have a look at this plus this, then we're going to get this very large number plus 128 at the end. So the small number went up in a step of all these zeros after the decimal point and then 1. And the large number went up in a step of 128. So the calculations generally depend on the relative precision of each floating point number. And in this case, the relative precision is 1 times 10 to the minus 16. So essentially we take a ratio of the unit in last place divided by the number. And we can see that this is times 10 to the minus 16 and this is times 10 to the minus 16. So a related function is going to be the next after function, which takes a number x and moves towards y and gives the next number after x in the direction of y. So for example, we take this number 1 times 10 to the 18 again, and we are moving higher up, so towards 2 times 10 to the 18, we can see what the next number after 1 times 10 to the 18 is. And since you already seen that the step was 128, then this is the next number. So this basically takes a number and then adds the number to the unit in last place. So the error due to float precision rounding can propagate when summing a sequence of floating point numbers. So there's a float sum function that carries out additional checks to combat these rounding errors. So if we take these numbers and compute the sum, we've got all these trailing zeros and then this 1. So this is a recursive rounding error. If we take the float sum of this, we get 0.9, which is more in line to what we expect. There is also the float absolute function, which is used to calculate the absolute value of a floating point number. So this is very similar to the absolute function in Python, except it always returns it as a float. So if we have a look at minus 0.3 and minus 0.3, the sign strip to 0.3 and 0.3 respectively. If we have a look at this using an integer, then we can see that this is now a float, whereas this is just an integer. So this hasn't been cast into a float. It's taking the input as an integer and returned integer with the sign stripped. So different programming languages have different implementations of the mod operator, and Fortran and C have a different implementation to the one that's inbuilt into Python. So there's a math.fortran mod function that computes the mod the same way that Fortran does. So if we integer divide pi by 3, we're going to get 1.0, and then there's going to be some sort of remainder. And this remainder can be calculated using the mod. So for a positive number, this is going to give 0.14159 and so on. And if we use the Fortran implementation, we get the same value. So the difference between the two implementations can be seen when a negative number is used. So if we have a look, we see a completely different number for the two implementations. So this is the negative of this number. And what this has actually done is it's went from 3 and subtracted this from 3. So the Fortran implementation has essentially done this, and the Python implementation has done this. So the math module also has a related remainder function, and this is typically associated with the round function. So it's the difference between x and the closest integer multiple of y, and this can be rounded up or it can be rounded down. So the remainder can actually be positive or negative. So if we take 10.5 and the float divided by 3, we get the value 3.5. If we round this, we're going to round up and get 4. So if we take 4 times 3, that gives us 12, which is 1.5 higher than 10.5. So 10.5 minus 12 is going to be minus 1.5, and that's the remainder. So in other words, it's 4 times 3 plus minus 1.5. So we've rounded the integer to 4, and then the remainder is minus 1.5. So if we instead have a look at 10.4 divided by 3, we're going to get 3.4666. And when we round this, we round down. So now the remainder is going to be positive. So it's going to be 1.4, and then all the zeros and 4. So in this case, we've got 3 times 3, which is 9, plus the remainder, which is 1.4, which gives us the value 10.4 as expected. So the math.remainder function also works with negative numbers, and a comparison can be made between the following functions. So first of all, if we integer divide, 10.5 divided by 3, so 3 3s are 9, and then there is 1.5 left. Because this is negative, you're actually going down to the previous negative integer. So this will give you minus 4 instead of minus 3. If we now have a look at the modulus, this is going to be 1.5. So if we take this together, minus 4 times 3 gives you minus 12. And minus 12 plus 1.5 gives you minus 10.5, and that's the value expected. If we have a look at the Fortran mod, we get minus 1.5. So here we can see we've got a different implementation. And if we have a look at the float division, then we get minus 3.5. And if we round this, we're going to get minus 4. So if we have a look at the remainder, we're going to get a positive remainder. So minus 4 times 3 is minus 12. Minus 12 plus 1.5 gives you minus 10.5. So the modulus fraction math.modf will split a float into a fractional and integer component, outputting a tuple. So it's quite similar to divmod, which returns a tuple with two values. In this case, it's going to return a fractional and integer part of x. So for example, if we have a look at the modulus fraction of pi, then we've got 3.0, which is the integer, although it's shown as a float. And then we've got this floating point number, which occurs after the decimal point. So both results carry the sign of x and are floats. So notice when you've got negative pi, that both of these are negative. So it can be quite confusing, this mod f and this f mod, so try not to confuse the two different functions. So we can also truncate a floating point number to an integer using the math.trunc function. So if we have a comparison to the round, minus 10.5 divided by 3 is minus 4. If we truncate this value, we're going to get minus 3. So in other words, all this stuff after the decimal point has just been chopped off when you've truncated it. And if we have a look at math.modf, and we have a look at the index 1, which is the second value in the tuple, we get minus 3.0. So notice the differences here. Here you truncated the value and you've chopped off everything past the decimal point. Here you've rounded it to the nearest number, which is minus 4. And here you've got the integer component, although this is expressed as a floating point number. So we also have the greatest common divisor, which will calculate the greatest common divisor between a sequence of numbers. So for example, we can have a look at the greatest common divisor of 128 and 12. So this gives the result 4, and 4 perfectly divides by 128 and 4. So notice in both cases there's no modulus. The lowest common multiple function also requires an input sequence of integers and returns the lowest common multiple. That is a number which can be divided by each number in the sequence without any modulus or remainder. So for example, we can have a look at 2, 3, 4, 5 and 8, and this gives 120. So if we have a look at the modulus of 120 and 2, the modulus of 123, the modulus of 120 and 4, the modulus of 120 and 5, the modulus of 120 and 8. This is all 0. The product function math.prod takes in a sequence of numbers in the form of a list of tuples and returns the product of all the numbers. So this is 2 times 3 times 4 times 5 times 8. And if we manually calculate this, we get the same value. The function math.copySign takes in two numbers, so x and y, and returns a number which has the magnitude of x and the sign of y. So if we have a look at this docstring, and we specify one number being the direction and the other being the magnitude, we can create a number with the magnitude of the first number and the direction of the second number. So this gives us minus 5.2 as expected. So there's a number of exponential and logarithmic based functions. So one of them is math.factorial, and we actually created our own version of this before. So recall that the factorial of 0 is 1, and it's not 0 because 0 multiplied by anything else would become 0, which would mean that every factorial would be 0. And the factorial of 1 is 1, so it's just 1. And the factorial of 2, which is 1 times 2, is 2. And the factorial of 3, which is 1 times 2 times 3, is 6, and so on. The value e was explored earlier. Now there's an actual function exp, which raises e to the power of x. So if we have a look at e to the power of 1, and we have a look at the exp function of 1, we get the same value. And if we have a look at e to the power of 2, and we have a look at the exp function with the input argument 2, we get the same value. So values on the exponential scale, as the name suggests, increase exponentially. So if we have a look at the exp of 1, we get this 2.71. The exp of 5 is 148, which is much larger. And the exp of 10 is 22,026, which is much, much larger. So sometimes it's useful to get the inverse of the exponential using the logarithmic function. Now the function log defaults to the natural base e by default. So if we have a look at the log of e, we should get 1 because these two essentially cancel out. And if we have a look at the log of e to the power 2, then we get 2 because these cancel out. If we have a look at the log of e to the 5, then we should get 5 because these two cancel out. So recall, we also use the decimal and binary counting systems quite commonly. So it's quite common to use base 10 and base 2. So if we have a look at 10 to the power of 0, we get 1. So what we actually want now is to obtain this value 0 from this value 1 and this value 10. So if we specify this as 1 and this as 10, then we get 0. And now if we have a look at 10 to the power 1, then we should get 10. And what we actually want is this 10 here and this 10 here, and we should get this 1. And 10 to the power of 2 is 100. So once again, we specify 100 here and then specify our base of 10, and we should get 2. And if we have a look at the base 2 to the power of 0 is 1, so we specify the 1 here and the 2 here, and we should get 0. So 2 to the power 1 is 2. So we've got a 2 here and a 2 here. So 2 here and 2 here, and we should get this 1. And if we have 2 to the power of 2, we should get 4. So if we specify the 4 here and the 2 here, then we should calculate this 2 here. So since these bases are so commonly used, they have their own functions, log 10 and log 2 respectively. And these both work as expected, yielding the same result as before. So the float radix exponent function is used to convert a fractional mantissa, an integer exponent, using a base of 2. So for example, if we have a look at its doc string, and we have a look at this number 0.125. What we've done is calculate a mantissa and an exponent. So the mantissa is going to be 0.5 and the exponent is going to be minus 2. Now if we take this mantissa and times it by 2 to the power of the exponent, we should get the original value, 0.125. and we see this works as expected. So the load exponent function is the inverse of this and is used to construct a floating point number from a mantissa and exponent using the base of 2. So if we have a look at its docstring, and we can provide the mantissa and exponent that we just calculated, and we get this same value as before. So it's essentially carrying this operation out. We've also got the exponential -1 function. So if we have a look at its docstring and reverse function, which is logarithmic +1, we can compare these to the standard. So if we have a look at the exponential of 1, we get this. If we have a look at the exponential of -1, then we're going to get 1.718, and if we add 1 to it, then we basically get the same thing. And if we have a look at the normal log function of 2 times e, then we get this value 1.69. And if we use log 1p, it's equivalent of 2e minus 1 here. So you see we get the same thing. So the math.factorial function operates on integers and therefore produces discrete integer values. There's an associated function called the gamma function. However, it takes an n+1 term opposed to an n term. So if we have a look at its docstring, and we have a look at the factorial of 0, and we have a look at the gamma value of 0 plus this offset of 1, we should get the same thing. Note that this is a floating point number, not an integer like this. Now if we have a look at the factorial of 1 and the factorial of gamma plus 1, we should once again get the same thing. We have a look at the factorial of 2 and the gamma of 2 plus 1, we should get the same thing. And if we have a look at the factorial of 3 and the gamma function of 3 plus 1, we should get the same thing. So we see we've got the same value in all cases, except this is a floating point number instead of an integer. And the gamma function can take in floating point values. So we can have a look at essentially the gamma value of 1.5 and then with this offset of 1. And this gives us this value here. So graphically, a comparison of the gamma function and the discrete values from the factorial looks like this. The factorial is essentially these discrete values, and the gamma function is a continuous distribution between all of these data points, and it's n+1. So for large values of factorials, the magnitude of the y-axis will change drastically, making it difficult to see the magnitude of all previous numbers when scaled alongside the last number. So notice that these all look essentially like 0 now, just because this number is so big. 3.5 times 10 to the 6. So you can see the scale has changed rapidly. So as a consequence, it's often useful to plot such large numbers on a log scale. And notice when you do so, you can see the changes of the small number. So this is 10 to the 0, which is 1, 10 to the 1, which is 10, 10 to the 2 is 100, 10 to the 3 is 1,000, 10 to the 4 is 10,000, and so on. So you get to see the differences in the small values quite readily, and you can see a lot more detail than what the linear graph shows for this specific data set. And there's also the log gamma function, so we can have a look at its docstring. So it's basically the log of the gamma function. And if we have a look at the factorial of 10, or the gamma value of 10 plus 1, we get the same thing. So if we take the log of these, then we're going to get this 15.1. And if we use the log gamma function directly, we're also going to get 15.1. So the remaining functions in the math module are generally related to geometry. And the function hypotenuse is an application of Pythagoras' theorem for right-angled triangles. So here you can see in the dot string, it's basically the square root of the sum of all the numbers squared. So the examples given is a 3, 4, 5 triangle. So in general, you've got a triangle which looks like the following. So this side is known as the hypotenuse, and it's a squared equals b squared plus c squared. So in order to get a, you're going to take this side and square it, and this side and square it, and then take the square root of them. So notice for this, because it's plotted on grid lines, you can basically measure the length of this as 1, 2, 3 boxes. So that's the length along x, and 1, 2, 3, 4 boxes, and it's the length along y. You can't measure this directly using boxes because the boxes aren't in the same orientation as the hypotenuse. So if we calculate this, then we get the length of 5, because it's a 3, 4, 5 Pythagorean triple. So what this means is you've got 3 squared, which is 9, 4 squared, which is 16, and that's 25, and the square root of 25 is 5. So the distance formula calculates the distance between two coordinates. So if instead of this plot, we just plot two coordinates, so remember you've got the coordinates going to be an x value and then a y value, so it's going to be 1, 1. And then it's going to be the x value and the y value, which is going to be 4, 5. So we can have a look at the distance formula, and basically it's asking you to specify the first coordinate and the second coordinate in the form of a tuple. So in other words, what we have here is this point 1, 1 and this point 4, 5. And under the hood, if we use Pythagoras' theorem, we've essentially got the same triangle as before. So this is going to be 3 squared, and this is going to be 4 squared, and this length should be the square root of 25, which is 5. So if we specify these two coordinates, we should get a distance of 5, and it works as expected. So the distance can also be projected to 3 dimensions and higher. So essentially, when this is done, a component of the difference for each axis is calculated, and this is depicted with the magenta cyan and sea green lines. So basically you've got a component along x, a component along y, and a component along z, and then you've got the distance from here to here, which is what you want to calculate. So this has the point 1 along x, 1 along y, and 1 along z. And this has the point 3, 4, 7, so it's 3 along x, 4 along y, and 7 along z, giving this. So the distance between these two is 7.0. And this can be calculated using 3 minus 1 squared, 4 minus 1 squared, 7 minus 1 squared, and then taking the square root of that, which gives the same thing. So we've had a look at Pythagoras' theorem, and it's a squared equals b squared plus c squared. On a 2D coordinate system, b can be represented by x and c can be represented by y. So what I mean here is this is the x value and this is the y value. And then this is the hypotenuse. Now if it's a circle, we're actually going to start at the origin, and this distance will be known as a radius. So let's actually have a look at a circle now. So circle begins at the origin, and every point on the circle has a constant radius. And if you have a look at a point is going to have a value along x, and it's going to have a value along y. So you can imagine forming essentially a right angle triangle. So you've got a hypotenuse here, and then you've got your value along x, and then you've got your value along y. And this is going to be a right angle triangle. So if we rearrange this equation, we've essentially got r squared equals x squared plus y squared. So remember, r squared was a squared, and x squared was b squared, and y squared is c squared. So this means we've got x squared plus y squared equals r squared, which is the equation of a circle. So let's have a look at the following phase diagram. Here, what we're doing is we're splitting the circle up into eighths. The red line indicates a radius. So we're starting at the origin, and it's a length of 1. So we've got some x value here and some y value here. And since we're using tau, it's normalized correctly, and a radian is the circumference here divided by the radius. And as mentioned, because this is a circle, any point on this circle is going to have a constant radius. And for simplicity, a unit circle is being examined, so this radius is going to be 1. So let's simplify the circle further by just looking at the first quarter of the circle. And we're going to use 16ths of tau. So notice we've essentially constructed this right angle triangle. So we've got this angle theta, we've got this hypotenuse, which is the radius, we've got some x value, and we've got some y value. So this is the opposite angle, the opposite length to the angle. This is the adjacent length to the angle, and this is the hypotenuse. And this is a right angle. So the point is depicted as a red circle, and notice it's on the fixed radius of 1, and it's on the circumference of the circle. So remember from high school trigonometry, you've got SO, CA, TOA. Sine of the angle is the opposite over the hypotenuse. The cos of the angle is the adjacent over the hypotenuse, and the tan of the angle is the opposite over the adjacent. So if we have a look at the sine of the angle, it's the opposite over the hypotenuse. This is a unit circle with a fixed radius of 1, so it's normalized. So this is effectively going to be the opposite over 1, which is going to be the opposite. So we can have a look at the sine function. Note that it's measured in radians. And we can have a look at the cos function. So the cos function is going to be, the cos of the angle is going to be the adjacent over the hypotenuse. Once again, the hypotenuse is 1, so this is going to get the adjacent. So if we have a look at the dot string, we can see once again that's measured in radians. So basically the sine of the angle is going to give this length, which is y, and the cos of the angle is going to give this length, which is x, and this is because we've got the radius being fixed to 1. The tan is the opposite over the adjacent, which is the sine over the cos. Once again, it's measured in radians. So let's just examine this quarter of the circle. So when tau equals 0/16 tau, we basically have this line here. So the radius is all going to be along x. So this means the opposite side is 0 and the adjacent is equal to the radius, which is 1. So therefore, the sine function of this angle should return 0 because there's no length here, and the cos should return 1 because all the component is along here. So we can check this, and then the ratio, which is sine over cos, should be 0 divided by 1, which should be 0. Next, let's have a look at that theta being 1/16 tau. So notice what's happened is this has moved up, this has got smaller, and this has got bigger. So now this should be non-zero and this should be smaller than 1. So we can check the size of these using the sine and the cos. And we see this has a length of 0.38 and this has a length of 0.92. And the tan is the ratio of these, so it's going to be this divided by this, which is 0.41. So let's now increase the size of the angle once again to 2/16 tau. So notice now that this right angle triangle essentially has an equal adjacent and opposite length. And this is due to the symmetry of the circle. So the values of these should be the same. So now the values of these are the same, and it's actually 1 divided by 2 to the power of 0.5. So because these two have the same value, at this angle their ratio should therefore be 1. And we see that this is essentially the case. This is the recursive rounding error of the floating point number. When theta is 3/16 tau, let's have a look at the triangle. So now notice that the opposite is the long length and the adjacent is small length. So we can calculate the opposite using the sine and the adjacent using the cosine. So this is 0.92 and 0.38, and the ratio, which is going to be the sine over the cos, is going to be 2.41. So if you've been observant, you'll have noticed that we've actually had these results before, and that's because there's some symmetry in the circle. So if we compare the angles at theta equals 1/16 tau and theta equals 3/16 tau. So here's the 3/16 tau that we've just looked at, and here's the 1/16 tau that we previously looked at. So basically notice that this is this angle here, and this angle is this angle here, and this length is this length, and this length is this length. So these are actually the same triangle, it's just in a different orientation. So we can see whether these are the same by using the math is close to function. And we can have a look at the sine of 3 tau over 16, i.e. this length, and see if it's close to the cos of 1 tau over 16, which is going to be this length. And we see this is true, so these two lengths are the same, and we can do the same for the other length. So we can have a look at the cos of 3/16 tau, and we can have a look at the sine of 1/16 tau. Once again, we see these are close to one another, i.e. these lengths are the same length. So if we have a look at 4/16 tau now, we see that we essentially have no adjacent and everything is along the opposite. So with no component along x and we've only got a y component, which is going to be equal to the radius, which is the length of 1. So this means the sine should be equal to 1, and the cos should be equal to 0. Now, in theory, you're going to be dividing 1 by 0, which is infinity. And this is 0, but it's shown using a very small number, and this is due to the recursive rounding error of the floating point number. And this isn't infinity, it's just shown as an incredibly large number. And again, this is due to the recursive rounding error of the floating point number. So you'll notice that this triangle or plane has symmetry, and we actually observed this earlier when we had theta equals 0/16 tau. So basically now at 4/16 tau, we've got the opposite being the entire component of radius, and when we had 0/16 tau, we had the adjacent being the full component of radius. So we can check essentially whether this value is the same as this, and they should both be 1. And we see this is true, and we can check the other value. So this should essentially be 0 along x or 0 along y. And we get true once again. So if we bring this information together, we can have a look at the length of the sine and magenta lines with respect to the angle theta. So here we see the value of the opposite side of the triangle as the angle increases. So if we just examine this once again, we started with a circle like here, opposite side was 0, then it increased a bit, then it increased a bit more, then it increased a bit more, and then finally it increased to the maximum length, which was the radius. So that's what you're seeing here. And here is the adjacent length. And if we have a look at this done the opposite. So it started at the full length here, and then it got a bit smaller, and then it got a bit smaller again, and then it got a bit smaller again, and then it's a length of 0. So notice the kind of mirror symmetry. This is going up, and then this is going down. So the above depicts the first quarter of a circle. So the above depicts the first quarter of a circle. Now a circle has symmetry in x and y. So if we have a look at the plot of a circle and we just take a single data point. Here we've got one data point, and if we take the x value, it's going to be positive here. If we take this data point mirrored, this x value is going to be negative. This x value is also going to be negative here, and the x value is going to be positive here. Now if we have a look at the y value, it's going to be positive. It's going to be positive here. It's going to be negative here. And it's going to be negative here. And this specific data point is mirrored here, 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 and here. So because it's in a mirrored data point and it's on a circle, it's always going to have a radius of 1, and the magnitude of the x and the y value are going to be the same because it's a mirrored coordinate. So what this means is that if we take the y sign, it's positive in the first quarter, so positive here, positive in the second quarter, then negative in the third and the fourth quarter. remember y is corresponding to sine. So this was the value is going to be the same, then the value is going to be negative, and then the value is going to be negative. We have a look at cos, which is going to be this coordinate here. It's going to swap sign. So it's going to be positive, negative. It's going to be negative again, and then positive again. So we take this value here, and then it's going to be the negative of the same value here, the negative of the same value here, and the positive here. So these all have the same magnitude, and these also have the same magnitude, because we've picked the point where x and y are also equal to one another. So if we have a look at the math.sine function, we can see we've got this positive, positive, negative, negative. So plus, plus, minus, minus. And if we have a look at the cos, we've got this positive, negative, negative, positive. Exactly as outlined here. So because a circle repeats itself, it's essentially going on the sign going to be positive, positive, negative, positive, positive, negative, negative, positive, positive, negative, negative. And if we have a look at the cos, it's going to be positive, negative, negative, positive, positive, negative, negative, positive, positive, negative, negative, positive. If we ignore this quarter 1a, for example, we see we've got this plus, minus, minus, plus, plus, minus, minus, plus. So if we ignore quarter 1, start quarter 2, quarter 3, quarter 4, and then do quarter 1, we see we've got plus, minus, minus, plus, which is the same as plus, minus, minus, plus. So it can be seen pictorially And if we have a look at the following pictorially, if you are essentially going from the x-axis, you've got this triangle. If instead you were going from the y-axis, you would have this triangle. But notice that the angle here and the angle here are going to be the same. And therefore the length here and that length are going to be the same. And this length are going to be the same. So this is the mirrored symmetry, and basically this means that there's a relation that sine plus basically a quarter of the circle is the cosine. So the angle plus a quarter of the circle is the cosine. So now that we've examined the symmetry, the three angles that we had a look at with the corresponding sines can be plotted across the remaining quarters of the circle. So we get something like this. So here's the y value, is starting from 0, going up to 1, then going back down to 0, and then down to -1, and then back to 0. Cosine's going from 1, going down to 0, then going to -1, then going to 0, and then going to 1. And notice that if you kind of ignore this first quarter, and then follow this trend, and then take this first quarter, you have this plot. So this is what the y and the x value look like as you go around the circle. And tangent is going to be this divided by this. So notice that this has the point 0 here and 0 here. And where it has 0 here, this has the value 1. And when it has 0 here, this has the value -1. Now, because the tan's a ratio of y over x, you're dividing 1 by 0 and dividing -1 over 0, which is technically plus infinity and minus infinity respectively. So in order to plot the tan, you need to constrict the axis so you can actually see it, because it goes up to plus infinity and minus infinity, so you're not seeing the shape. And this is why it's discontinuous here and discontinuous here. So combining the plots will give something like this. So you can put the sine and the cosine together on the same plot with the tan below. And sometimes it's useful to, instead of have this 0/16 tau to the left, to have this in the center. So therefore you express this in negative terms and this in positive terms. So you've essentially got this 0 point, and notice that this is kind of straight and then it deviates as you get away from the center. So for a circle centered around the origin with a radius 1, every point can be considered as a right angled triangle with a constant hypotenuse of 1 equal to the radius. So recall the circle equation is essentially an application of Pythagoras' equation. And in the case of a unit circle, r is equal to 1, x is equal to cos theta, and y equals sine theta. So what this means is you've got this identity, cos squared theta plus sine squared theta equals 1 squared. So this is cos squared theta plus sine squared theta equals 1. And we can plot out the squared terms, and you'll notice that 1 plus 0 is 1, and then this plus this is going to be 1. And the two data points are here, both 0.5, so it'll be 1. And you can basically see across everything else, due to symmetry, that every data point is 1. And this is what the y squared over x squared will look like. Recalling these will go to infinity squared in both cases, which is infinity. So we've also got the arcsine, arccosine, and arctangent functions, which essentially perform the opposite, i.e. retrieve the angle from the following ratios. So we can have a look at their docstring. One thing to notice is that this is measured in radians, and you've got a result between two specific angles. Notice that this has a different range, and if we have a look at the docstring of the tan, this follows the same range as the sine. Okay, so if we focus on the sine, we see the ranges between minus pi over 2 and pi over 2. Remember, pi is tau over 2, so this is going to be minus tau over 4 and tau over 4. And because we're expressing this in sixteenths, we're going to use minus 4/16 tau and plus 4/16 tau. So if we plot the sine curve over this range, we see we've essentially got a unique value at every angle. Outside this range, it repeats, so that's why we constrict this range, so we have a unique angle for each value. And notice that it's basically negative here and positive here, and this is 0, and it's very flat here. And this is what the tan looks like at that range. So we'll keep expressing the angles as 1/16 tau, and we can have a look at 5 values returned by the arcsine function. So if we basically have a look at the value minus 1, we should get this. So we've essentially picked the 5 values. Here, minus 1, this one, this one, this one, and this one. and we see we get these in 16ths tau, which match the x-axis as expected. So if we have a look at this function again, the sine theta plus 4/16 tau equals cos theta, we can take these original limits and we can add 4/16 tau, and then this is going to give us 0/16 tau, 2 plus 8/16 tau, and here we're going to plot the cos. So notice that this starts at 1 and this goes down to -1, and this is at 0, so it's again very flat here, and then it deviates as you get away from the origin, from a straight line. So once again we can just test these 5 points here, and we can express the values in 16ths of tau. So when this is 1, we should get 0. And we see we get exactly what we expect for these 5 data points. This one, this one, this one, this one, and this one. So since the sine is the default, the arctan function operates over the same range as the arcsine function. So we can test the values here. It's going to be -infinity, -1, 0, 1, and infinity. So if we have a look here, it's going to be here, 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 and here, and this is going to be -infinity and +infinity. So once again, we've got the -4, -2, 0, 2, and 4 as expected. So there's another function, arctan2, which takes in 2 separate input arguments, y the opposite value and x the adjacent value, instead of the ratio directly. So we can see that this essentially works in the following way. So if we just take the position where they were both equal, then the ratio between the two sides is 1. And these two give the same result as expected. So if we examine this, we notice that this is 0. And this is essentially a straight line close to angles of 0. And we get more and more deviations as we go away from 0, and this becomes nonlinear here and here. So this has some importance because the error function essentially looks a bit like that. So to understand the error function, we need to have a look at the normal distribution. The normal distribution has a mean mu of 0 and a standard deviation of 1. And it's got normalization factor 1 over square root of tau, and then it's got exponential minus x squared over 2. So this is normalization factor, and recall that exponential of 0 is 1. So the value at the origin will be this normalization factor multiplied by 1. And then the minus x squared term in the exponent will rapidly diminish the value of y as the value of x becomes further and further away from the origin. So there's no inbuilt function for the normal distribution in the math module, but we can easily construct it just by returning this mathematical expression. And then we can just test it at some values of x. and we can essentially plot this normal distribution. So here's the normalization factor, and you can see that it rapidly decreases down to 0 on both sides. So each standard deviation is 1 over the square root of 2 in terms of x units. So we can plot the first, second, and third standard deviation here. So visually, if we have a look at this curve and we count these number of boxes underneath the curve, there's approximately 20 boxes underneath this curve. So you've got 20, and the length is 1 times 0.05. So 20 times 0.05 times 1 is 1, so this is normalized. Now, if you were to have a look at one standard deviation, you can see that the positive bound encloses about 6.5 boxes, and the negative bound also encloses 6.5 boxes. So if we just take this as being 6.5 plus 6.5 divided by 20 is 0.65. Actually, it's slightly larger, and you've basically got 68.3% chance of a value lying between one standard deviation. If we have a look at two standard deviations, we've essentially got 3 other boxes here and 3 other boxes here. So that gives us 19 out of 20, which is 0.95. So we've got approximately 95% chance of lying within 2 standard deviations. And if we have a look at 3 standard deviations, it's approximately another box on either side. So we can see that this is basically 20 over 20, which is 1. It's not quite 1, there's actually a small amount here and a small amount here, so it's 99.73. And quite often a value is quoted with a mean and an error. That means it's between 3 standard deviations, and that means you're 99.73% likely to find it within this boundary. So the error function has this formula. So initially it may look quite complicated, but it's a formula that essentially finds the area under the curve of the normal distribution, which is depicted above using integration. So the formula takes in x as an input argument and returns twice the area under the curve between x and 0, and this accounts for the positive and negative bound. So if you just consider the positive direction and multiply it by 2, because this is mirrored, you can do that. So let's have a look at one standard deviation. We get 68.3. 2 standard deviations, we get 95%, and 3 standard deviations is this 99.7%. So it's worthwhile visualizing both of these together. So this is the normal distribution, and this is the error function. So you can see the first, second, and third standard deviation. So while the probability here was basically the total area under the curve, you can see this is the probability as you move away from 0. So if you just consider the positive side, within 3 standard deviations, you're 99.7% likely to have the value. Also the complementary error function, which is basically the probability of not being in the bound, i.e. the probability of being under this tail. So this is slightly less than 1, so what is your probability of being here instead of within here. So that's what the complementary error function does. So we can plot this as well. And generally we are only focusing on the positive values. So the probability when you're at the peak of it being anywhere here is going to be 1. And the probability you're at here is going to be basically the height of this area here. So we can have a look at its docstring, and we can just see that it's related 1 minus the normal error function will give this, and the complementary error function gives this. So we can see that they're simply related to one another. So this is 1 standard deviation, 2 standard deviations, and 3 standard deviations. So this is the chance of not lying within 1 standard deviation, the chance of not lying within 2 standard deviations, and the chance of not lying within 3 standard deviations. So the sine, cos, and tan functions modeled the unit circle equation. And recall, this basically looked like this, and you created this right angle triangle with angle theta, an opposite, adjacent, and a hypotenuse. So the unit parabola is similar to the circle equation. Notice, however, the sign is negative here. So if we have a look at this plot, it's going to look something like this. So towards here, you've basically got a straight line, and you've got a straight line here where x equals y and y equals x. Kind of interesting part happens along here, which you can't really see if you see the full parabola. So towards these limits, you've got your straight line, and towards here, you've got deviation from a straight line. So if we zoom in, we can see the deviation. So this is zoomed in between 4/16 tau and minus 4/16 tau, and basically this is 4, 3, 2, 1, 0 tau, minus 1, minus 2, minus 3, minus 4 tau, all over 16. So the hyperbolic sine, hyperbolic cos, and hyperbolic tan functions are the hyperbolic counterparts to the circular functions sine, cos, and tan. So the angle is once again being formed between the origin and the point on the parabola. You've once again got an opposite, which is going to be your y, and you've got an adjacent, which is going to be your x. So once again, the sine of the theta is going to be the opposite of the hypotenuse, and we're going to consider a unit parabola. So this is going to be the opposite over 1, which is the opposite. And cos is adjacent of the hypotenuse, which is, in the case of a unit parabola, going to be the adjacent over 1, which is the adjacent. So the x and y values can therefore be checked at the minimum of the unit parabola. So it's 1 and 0. So here you see x is 1 and y is 0. So this is 0 and this is 1. And it can also be checked near the minima. So at 1/16, we can see this is 108, and we see this is 0.42. So we can see that this is slightly below a half, and this is slightly above 1. and we can check it at 4/16 tau. So we see these are more similar. So we can just see that this is slightly below this, which is y equals x. So that means that this is just slightly smaller than this. So towards the limits, you're essentially getting the same value of x and y. And this is a way out here. The hyperbolic tangent is the ratio of these two lengths. And at the origin it's going to be 0 because it's 0 divided by 1. And towards the edge it's going to essentially be 1 because both lengths are pretty much identical. So now that we've got an understanding of these, we can plot the functions. And they look like this. And to view the nonlinearity in more detail, we can examine the smaller angles. So it has this kind of form. So recall the unit parabola was defined using the equations x squared minus y squared equals 1. And since we've got our definition of x and y, and the radius is 1, then we've got cos squared theta minus sine squared theta equals 1. And this offset can be seen when the square functions are plotted. So it's this minus this, which is 1. This minus this is also 1. This minus this is also 1. It's also 1 in other places, but visually it doesn't look it just because of the shape of the curves. So the cos and the sine equations are related to the exponential, which previously some intuition was built upon. So it's the positive exponential of the angle and negative exponential of the angle divided by 2. And this is the positive exponential minus the negative exponential divided by 2. So at theta equals 0, you can see that this is essentially 1 plus 1 divided by 2, which is 1. And in the case of the sine, it's going to be 1 minus 1 divided by 2, which is 0. So that gives us the coordinate x equals 1, y equals 0 as expected. And for large values, it's insightful to plot out the positive exponential and negative exponential components. So at larger values, the positive exponent dominates because it goes exponentially higher, and the negative exponent goes exponentially lower. Okay, so we've got the sandy, brown, and pale green curves. So in the small region, when they're added, this is going to be significant at the start, and then it's going to go down effectively to 0, and this is going to go to a very large value because this exponentially increases and this exponentially decreases. So you've got the value 1 when they combine, and then you're going to see the effect of this going down, and then eventually this is just going to dominate. So that's the cos hyperbolic function, and the sine hyperbolic function. You've essentially got the difference between these. So the difference between this and this is going to be 0, and then as this exponentially increases, and this has less and less effect, the effect of this being pulled down by this is going to become negligible. So we can plot these out. So this is the y term and this is the x term. So that's an overview of all the functions in the math module. There's an associated complex math module. So recall that the square root of a negative number is indeterminate using only real numbers. So what happens is we introduce this term j, which is used to represent an imaginary number. This is effectively 0. It's the recursive rounding of a floating point number. And this is 1 j. So that's the definition of j, it's the square root of -1. So if we take 1 j times 1 j, we're going to get -1 because its definition was being the square root of -1. So if it's squared, then you're going to undo this. So a number with a real and imaginary component can be created using the following. So in order to visualize this, use an XY grid with X representing the real axis and Y representing the imaginary axis. So basically you've got this number, any real number would just be lying along this real axis. So you've got a real component of 3, but this also has an imaginary component of 2. So we treat this number as effectively being a coordinate. And it's got two attributes, the real attribute and the imaginary attribute. So that's the 3 and that's the 2. So addition of two complex numbers involves addition of the real components along the real axis and addition of the imaginary components along the imaginary axis, using similar mathematics to vectors. So what we have is 3 minus 2, which is 1, and we have 2 plus 1 is 3. So when we add them together, we've got 1 plus 3j. And this can be conceptualized in a plot. So you basically started here, and that was your original real component, and that was your original imaginary component. Then you took this away from the real component, and you added this to the imaginary component. So you went from here and ended over here. So similar arithmetic is carried out for subtraction. For multiplication of two numbers, j should be treated as an algebraic variable and brackets should be multiplied out. So this is going to be 3 times minus 2, and it's going to be 3 plus 1j. It's going to be 2j times minus 2, and then it's going to be 2j times 1j. So this is going to give minus 6 plus 3j minus 4j plus 2j squared. So minus 6 minus 1j plus 2j squared. J squared is minus 1 because that's the definition of j. So minus 6 minus 1j plus 2 times minus 1. Combine the real terms and the imaginary terms gives minus 8 minus 1j. And this can be done in Python using the multiplication operator star. And there's a special number that can be multiplied with the complex number to obtain only a real component. And this number is known as the complex conjugate. So we can have a look at num1 and we can have a look at its conjugate. So you essentially flip the sign here. And then if you have a look at the magnitude of the multiplication between a number and its complex conjugate, we've got 3 times 3 plus 3 times minus 2j plus 2j times 3 plus 2j times minus 2j. So we've got 3 times 3 plus 2j times 3 minus 2j times 3 minus 4j squared. So these two cancel out. So you've got 9 minus 4, j squared is minus 1. So this is 9 minus 4 times minus 1, 9 plus 4, which is 13. Notice this is a real number with no complex component on it. This can be done in Python using the following. So in general, a complex number is considered to have the general form z equals x plus iy. And if we take x to be 1 over the square root of 2 and y to be 1 over the square root of 2, then we can represent this number once again on a circle. So this looks very similar to what we had before when we looked at the sine, cos and tan functions. This angle is called phi instead. This is the real component and this is the imaginary component. And this is radius. And just for clarity, this is the plot we had earlier on. So you can see that they're pretty much identical. So for a complex number, r is the radius of the circle, or more generally, it's known as the magnitude of the complex number. And phi is the angle the vector makes with the origin. So we've got x equals r cos phi and y equals r sine phi. And therefore, z is going to be of this following formula: r sine phi plus j cos phi. So a complex number times its complex conjugate should square the magnitude of the complex number, leaving only a real component. So we can test this out. So we're going to have these 4 terms. Then we've got the sine squared term. These mixed terms cancel out, and then we've got the cos squared term. Then the j is squared, so this becomes -1. So you've got sine squared plus cos squared phi, and you've got r squared. Recall that this was equal to 1, so this just gives r squared. And this condition is also satisfied with a complex exponential. So if we take this complex exponential and times it by this complex exponential with the sign change, then you've got r squared and then the exp of this minus this, which gives r squared the exponential of 0, which is 1, which it gives r squared. And equating these together essentially gives Euler's formula, and therefore z equals r exp j phi. So the complex math module CMath can be imported using the following. So once it's imported, a large number of identifiers can be seen. And you'll notice that most of these identifiers have the same name as the identifiers in the math module. So they're essentially the same identifiers, but have been modified to work with complex numbers. So we can view the help in a bit more detail. And we see that there's slightly more constants and slightly more functions, but most of them are the same. They just scale up to a complex number. So we can have a look at the directory and we can group these into constants. So we've got a constant for an infinity imaginary component and not a number imaginary component. We've got the same constants as before otherwise. Have a look at the mathematical functions. We see that most of these are the same as before. There are some other ones like polar and rectangle coordinates as well as the phase. But the same data model attributes and methods as before. So the complex math module is similar to the math module. So if we have a look at the square root, for example, we're going to return the square root of the rational number x. Whereas if we have a look at the complex square root, we're going to return the square root of the complex number z. So we can just test this out using a complex number. So the mathematics is harder to work out on pen and paper with a complex number than it is with a real number. So if we consider the complex number num1, 3 plus 2j, and we plot this out on a circle, we can see it's this red dot. So it's got a radius r and an angle phi. So here we've got the length x, which is 3, and y, which is 2. And these grey dots are just divisions, 1 over 16 tau. So you can see that this is 1 and this is 2, so this is pretty much 1.5. So this complex number z can be expressed in xy coordinates, or it can be expressed using r or phi coordinates. So recall the two forms. So the complex math phase function can be used to return the phase from a complex number in the following format. So if we have a look at num1, it's 3 plus 2j, and the complex angle can be calculated using the phase. So this is equal to the maths.atan of the y to x ratio, and we see that we get the exact same value, because remember, you're calculating the opposite over the adjacent here, and then you're getting the angle for that. So this is the angle in radians. It's converted to 16ths over tau, and we get 1.5, which is exactly as depicted in this diagram. The related function polar will return the radius and the angle in the form of a tuple. So if we have a look at the same number, we get the radius here, and we also get the angle here in radians. So this is essentially calculated using the Pythagoras' theorem, so it will be this squared plus this squared. So we can check this out using Pythagoras' theorem to get the hypotenuse, and we get the same value. So the function complex maths.rect does the inverse and returns a complex number in rectangular coordinates from a tuple of the form r phi. So for example, if we just use the same values as before, then we're going to retrieve our original value. And this has got a recursive rounding error because each component is a floating point number. So the functions in the maths and complex maths module are designed to work with a scalar. So this is a scalar, and if we run the function, we get a scalar value returned. So sometimes it's convenient to broadcast such a function to an inbuilt collection. So I can use list comprehension to create a series of angles. So they're going to basically be in tau over 16 steps, and it's going to range from -8 over tau to 9 tau over 16 in tau over 16 steps. And we're exclusive of the upper bound, so the last value is going to be +8 over tau. So if we have a look at angles, we've got them here, and we can use the built-in map to map a function to an iterable. So we can map this sine function to this list of angles. This gives a mapped object. This mapped object can be cast into a list, and it will retrieve the sine of each of these angles. So you can see a similar kind of trend to what was previously explored with the plots. And essentially this data was used to make the plots. This can also be done with a function that requires multiple input arguments. So when we had a look here, we just had a look at a single point. If we want the xy positions of all of these angles, we know what the size of the radius is, it's fixed, and we know where all of these angles are. So what we can do is just create less comprehension of constant radius, and we've already got the angles from earlier, so we can use the complex math function rectangle to give them real and imaginary components for each of these angles. Since this radius is a constant, a repeating iterator could also be used. So from iter-tools we could import repeat, and we could create this constant iterator. And we could use this constant iterator here to basically get the same thing. So the syntax for broadcasting using Python standard libraries becomes a bit convoluted, and this is only broadcast to a single dimension. Normally, mathematical expressions are broadcast using ND arrays with the third-party Python library NumPy, which is a numeric Python library. This needs to be imported separately. So you've got a number of functions in NumPy to create linear spaced arrays. So we can use that to create a linear spaced array, which is a bit cleaner than the list comprehension above. And then we can just use numpy.sine. So this actually uses the sine function within the math module, but broadcasts it to a NumPy array using much simpler syntax. And we can also have a look at the cos, which broadcasts the maths cos function to a NumPy array. And we can also have a look at creating a 2D array. So we're going to have a θ1 and θ2 axis. And we can also broadcast this using the same math function. So using this similar syntax, this is broadcast to a two-dimensional array.